8.2 Proving divisibility results. You can use proof by induction to prove that a given expression is divisible by a certain integer. And you may recall from what we discussed in the previous video, the steps in a proof by induction problem. We've got our first step, the basis step, where we prove the general statement is true for n equals 1. We then move on to our assumption step, where we assume the general statement is true for n equals k. We then move on to our inductive step, where we show that the general statement is then true for n equals k plus 1. And finally, for our conclusion step, this is a general statement which shows that the result is true for all positive integers n. Example number 4. We have to prove by induction that for all positive integers n, 3 to the power of 2n plus 11 is divisible by 4. Well, if you recall, using our steps which we discussed before, we begin with our basis step. So, we start off with step 1, where we see what happens when n is equal to 1. So when n is equal to 1, we first of all let f of n equal this result over here. So we will let f of n equal 3 to the power of 2n plus 11, and so f of 1, that's equal to 3 to the power of 2 lots of 1 plus 11. So we've got 3 to the power of 2 plus 11, 9 plus 11, that's 20, 20, that is 4 lots of 5. Of course, 20 is divisible by 4. So that's what we write down over here. And then you may recall for our second step, that's when we assume that the result is true for n equals k. So for step 2, we will assume that the result is true for n equals k. In other words, f of k equals 3 to the power of 2k plus 11 is divisible by 4. Now, with these divisibility results, we need to be a bit careful when we come to our third step. And just as a reminder of what our third step is, that's the inductive step, where we will show that the general statement is true for n equals k plus 1. So, step 3, we will see what happens for f of k plus 1, and our goal over here is to show that f of k plus 1 is divisible by 4. So, f of k plus 1, that's equal to 3 to the power of 2 lots of k plus 1 plus 11. Now, over here, the idea is over here, before we move on any further, is to get this line over here similar to what we have over here. Now, what do we mean make it similar? Well, if you pay attention over here, we've got a 3 to the power of 2 lots of k plus 1, and here we've got a 3 to the power of 2k. Now, how do we make those similar? If I expand on the top, we've got 3 lots of 2k plus 2 plus 11. Now, we can rewrite this as 3 to the power of 2 times by 3 to the power of 2k, and then we still add on this extra 11. This now is similar to what we have over here. The only difference is this time, we've got the 3 to the power of 2k being multiplied by 3 squared, which is 9. So we've got 9 lots of 3 to the power of 2k plus 11. So this is our third step. We have made f of k plus 1 over here similar to f of k. And now, to continue on with this over here, we will now work out f of k plus 1 minus f of k. And there's a specific reason we're going to be doing this, which you'll see. If we work out the difference between these, we've got f of k plus 1, which is 9 lots of 3 to the power of 2k plus 11, minus f of k over here. So maybe if we show these in brackets, f of k, that's 3 to the power of 2k plus 11. Now if we continue from here, we've got 9 lots of 3 to the power of 2k minus 3 to the power of 2k. You can see over here, that's 8 lots of 3 to the power of 2k. And plus 11 minus 11, that's 0. So f of k plus 1 minus f of k, that's 8 lots of 3 to the power of 2k. And essentially, we know in the question, eventually we want to show that f of k plus 1 is divisible by 4. And you'll notice over here, the 8, that's 4 times by 2. So here we've got 4 lots of 2 lots of 3 to the power of 2k. And of course, expanding this out gives this result over here. And finally, for us to get f of k by itself, we need to take this f of k to the right hand side. So we've got f of k plus 1, which is equal to f of k plus 4 lots of 2 lots of 3 to the power of 2k. Now, we already know that f of k from our second step, this is divisible by 4. And we've got 4 times by something else. This over here is divisible by 4. So therefore, the entire thing is divisible by 4. Okay? So now, for our fourth step, we move on to the conclusion step. So just as a reminder, that's just a general statement which tells us that the result is true for positive integers n. So therefore, for step 4, if we write down our conclusion step, if f of n is divisible by 4 when n equals k, so that's our assumption step in step 2 over here, then it's been shown through mathematical induction that f of n is divisible by 4 when n is equal to k plus 1, and we saw that in the third step over here. This result is divisible by 4, this result is divisible by 4, so the entire thing is divisible by 4. And as f of n is divisible by 4 when n equals 1, that's from our first step, we can conclude that f of n is also divisible by 4 for all positive integers n. Example number 5, we have to prove that for all positive integers n, n cubed minus 7n plus 9 is divisible by 3. Well, for the first step, step 1, we will show that the result is true for n equals 1. So, first of all, let f of n equal n cubed minus 7n plus 9. So therefore, f of 1, that's equal to 1 cubed minus 7 lots of 1 plus 9. If we work all of this out, we get 3. And of course, 3 is divisible by 3, as we see over here. And our second step, step 2, we will assume that the result is true for n equals k. So in other words, we will assume that when n equals k, f of k, which is equal to k cubed minus 7k plus 9, is divisible by 3. And for our third step, the inductive step, we will see what happens when n is equal to k plus 1. So when n is equal to k plus 1, f of k plus 1, that's equal to k plus 1 all cubed minus 7 lots of k plus 1 plus 9. And the idea over here is to make all of this similar to this before we move any further. So let's expand the k plus 1 all cubed. we get k cubed plus 3k squared plus 3k plus 1, and then we've got minus 7k minus 7 plus 9. So if we tidy all of this up, we get k cubed plus 3k squared minus 4k plus 3. So these two are similar to each other. They're not exactly the same, but they're similar to each other in that they both have a k cubed in them. So with any divisibility result, let's now work out the difference between f of k plus 1 and f of k, just as we saw in the previous example. So f of k plus 1 minus f of k, we've got f of k plus 1, I'll put all this in a bracket, we've got k cubed plus 3k squared minus 4k plus 3, and then we've got f of k, which is k cubed minus 7k plus 9. So if we tidy all of this up, well, we've got k cubed minus k cubed, that's 0k cubed. Then we've got 3k squared minus 0k squared, so here we have 3k squared. Then we've got minus 4k minus 7k, so that's plus 3k. 3 minus 9, that's minus 6. And what we can do, well, we want to show that this is divisible by 3. So what we can do over here is take out a 3 as a common factor. So we've got 3 lots of k squared plus k minus 2. And now if we take this f of k to the right hand side, we can therefore conclude over here f of k plus 1, which we want to show is divisible by 3. This is equal to f of k plus 3 lots of k squared plus k minus 2. Because over here this result is divisible by 3, we already know from our assumption step this result here is divisible by 3. So the entire thing is divisible by 3, and that's exactly what we wanted to show. So from this we can move on to our conclusion step, step 4. And in step 4, for our conclusion step, we have the following. If f of n is divisible by 3 when n equals k, then it has been shown by mathematical induction that f of n is also divisible by 3 when n is equal to k plus 1. And because the result is true is divisible by 3 when n is equal to 1, the entire thing is also divisible by 3 for all positive integers n. Example number 6, we have to prove by induction that for all positive integers n, 11 to the power of n plus 1 plus 12 to the power of 2n minus 1 is divisible by 133. Now this is a much more difficult example, but the steps remain the same. For the first step, where we see what happens when n is equal to 1, we first of all let f of n equal this result here, 11 to the power of n plus 1 plus 12 to the power of 2n minus 1. So when n is equal to 1, f of 1 is equal to 11 to the power of 1 plus 1 plus 12 to the power of 2 lots of 1 minus 1. We have 11 to the power of 2 plus 12 to the power of 1. 121 plus 12, you'd find that to be 133. 133, that is divisible by 133, as we see over here. For our second step, that's the assumption step, where we will assume that this result over here is divisible by 133 when n is equal to k. So we will assume that this result is true when n is equal to k. In other words, f of k equals 11 to the power of k plus 1 plus 12 to the power of 2k minus 1 is divisible by 133. For our third step, we will see what happens when n is equal to k plus 1. So if we work out f of k plus 1, we have over here 11 to the power of k plus 1 plus 1 plus 12 to the power of 2 lots of k plus 1 minus 1. And our goal over here is to make this line over here, first of all, similar to what we have over here in our assumption step. So here we have an 11 to the power of k plus 1. Somehow here we will also want to get an 11 to the power of k plus 1. And using the laws of indices, indeed we have 11 to the power of 1 multiplied by 11 to the power of k plus 1. Of course, adding the powers gets this result here. And over here, if we expand on the top, we have 2k plus 2 minus 1. Now to make this similar to what we have over here, we've got a 12 to the power of 2k minus 1, and we can get that by using the laws of indices. We have over here 12 to the power of 2 multiplied by 12 to the power of 2k minus 1. And of course, adding the powers, because we've got the same base, gives this result here. So we have 11 lots of 11 to the power of k plus 1 plus 12 to the power of 2 lots of 12 to the power of 2k minus 1. So we've got 11 lots of 11 to the power of k plus 1 plus 144 lots of 12 to the power of 2k minus 1. Now that we've done this, we now need to work out f of k plus 1 minus f of k. So f of k plus 1, that's over here. Let's just copy that out. We've got 11 lots of 11 to the power of k plus 1 plus 144 lots of 12 to the power of 2k minus 1. And then we subtract off f of k. F of k over here is 11 to the power of k plus 1 plus 12 to the power of 2k minus 1. Now if we tidy all this up, we have 11 lots of 11 to the power of k plus 1 minus 1 lots of 11 to the power of k plus 1, so that will be 10 lots of 11 to the power of k plus 1. Then we've got 144 lots of 12 to the power of 2k minus 1 minus 1 lots of 12 to the power of 2k minus 1, so that will be 143 lots of 12 to the power of 2k minus 1. Now, the difficulty over here is recognizing what we're trying to prove. We're trying to prove that this result over here is divisible by 133. So you need to show that this expression somehow is divisible by 133. And the way to do that is to recognize over here the 143 we can rewrite as 10 plus 133. Now why do I say 10 plus 133? Well, first of all, we want to show that the result is divisible by 133, and also here we've got a 10. So we've got 10 lots of 11 to the power of k plus 1 plus 10 lots of 12 to the power of 2k minus 1 plus 133 lots of 12 to the power of 2k minus 1. And of course the 10 plus the 133 gives the 143. Now why did I do this? Well, this result obviously here, all of this is divisible by 133. And somehow we need to show that this result here is also divisible by 133. How can we do that? Well, over here, if I take out a 10 as a common factor, we've got 10 lots of 11 to the power of k plus 1 plus 12 to the power of 2k minus 1. And if we expand this out, we get this result here. And then we add on 133 lots of 12 to the power of 2k minus 1. Now, 11 to the power of k plus 1 plus 12 to the power of 2k minus 1 you'd notice in step 2 that's what f of k is. So here we've got 10 lots of f of k plus 133 lots of 12 to the power of 2k minus 1. And we can therefore conclude over here f of k plus 1, that's equal to, well, if I take this over to the right hand side, we've got 10 lots of f of k plus 1 lots of f of k, so that's 11 lots of f of k, and then we've got 133 lots of 12 to the power of 2k minus 1. And of course this entire thing will be divisible by f of this entire thing will be divisible by 133. Why is that? Well, clearly this result here is going to be divisible by 133. We've got 133 times something, that's going to be divisible by 33. We've assumed over here f of k is divisible by 133, and that's from step 2 over here. So 11 times by something divisible by 133 will also be divisible by 133. So this entire thing is divisible by 133. And therefore, we now need to move on to our fourth step, the conclusion step. And with our conclusion step, we have the following. If f of n is divisible by 133 when n equals k, then it has been shown that f of that f of n is also divisible by 133 when n equals k plus 1. And as f of n is divisible by 133 when n equals 1, it has been shown that this entire thing is divisible by 133 for all positive integers n. So over here, you need to recognize, if we go back to our previous steps, once we've done our assumption step, we first of all work out f of k plus 1. We try to make f of k plus 1 similar to f of k over here. And once we've done that, we find out the difference between those, and then we can simplify. And if you get something looking like this, then to show that this thing is divisible by a certain result, we need to rewrite the result. So over here, we want to show that this thing over here was divisible by 133. So we rewrote the 143 as 10 plus 133. And happily for us, when we did that, here we had a 10. Here we've got 10. We could factorize that out over here. So we've got 10 lots of this thing, which happily for us was f of k. And then this thing over here was divisible by 133. And then taking everything over to one side, we showed that the entire thing is divisible by 133.